In this lecture, we will derive the total force on an electric dipole when it is placed in a external electric field. We will also try to derive the expression for the potential energy of this dipole when it is placed in an external electric field. So let us say that this dipole, this is minus q charge, this is plus q charge, and this is d, is placed in an external electric field E. So the force on dipole can be written as sum of the force on the plus q charge and the force on minus q charge, or minus q charge into the electric field at minus q charge plus the plus q charge and electric field at plus q charge. Now using Taylor series expansion, I can write the field at plus q charge in terms of the field at minus q charge as E at plus is equal to E at minus plus dou by dou L of E at minus into D, or I can further simplify it as dou by dou N of E into dou N by dou L into D. Now let us say these are two surfaces. This is the normal between them, and this is DL, and this is angle theta, and this is DN. So you see that DN by DL is equal to cos theta. So I can write E at plus charge is equal to E at minus charge plus dou E by dou N cos theta into D. So QE plus can be written as QE minus plus Q into D cos theta dou E by dou N. So the total force on the dipole is equal to minus QE plus QE at minus plus QD cos theta dou E by dou N. Now this is nothing but the gradient, because it is the maximum rate of change and its direction will be in the gradient direction. So in vector form I can write it as F is equal to, this is QD, in vector I will write it as P dot del into the electric field. So this is the expression of force. Now you see that if E is uniform, then what will happen? This term will be equal to 0 because there will be no spatial variation. So this force will be equal to 0. So in a uniform applied field or external field, the total force on dipole is equal to 0. It implies there is no translational acceleration of the dipole. There can be a torque on the dipole, but there will not be any translational acceleration on the dipole. So you see that we have derived the expression of the force on the dipole as P dot del into E. Now I will try to make an expression for the potential energy of this dipole. Let us see how to do that. So we will expand P cross del cross E. So I will use back cab rule. So it will be E del dot P minus or back cab rule means del P dot E minus C del dot P, or again I have done a mistake, P dot del. So writing in proper sense, it will be del P dot E minus del P dot del E. As I told earlier that whenever we have operators, we have to see the sequence of operation. So instead of back cab rule, we actually have BAC minus ABC rule. So this is the form. So you see that this P dot del E can be written as del of P dot E minus P cross del cross E. Now for electrostatic field, this is equal to 0, del cross E is equal to 0. So for electrostatic field, P dot del E, which is actually equal to the force on the dipole, is equal to del of P dot E. So we can see that in an electrostatic field, The force on the dipole is given by the gradient of some quantity, and that quantity is P dot E. Now if I define that minus of P dot E is equal to some U, then I can see that F is equal to minus of del U. So in this way we can see that force on a dipole can be found as a gradient of a quantity U, where this U is actually defined as minus P dot E. So by this definition we can see that it is a potential energy. So this is the potential energy of the dipole in an external electrostatic field. So in this way we have defined or derived two terms. First one is the electrostatic potential energy of a dipole. It is given as minus P dot E. And the second one is the force on the dipole. It is given as P dot del into E. We could have derived this expression using torque on the dipole, but this is more general expression, or the way of derivation is more general. So I would prefer to give this derivation instead of the derivation which is usually found in other books. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.